Let's talk some set theory. So 1.1 is about sets, subsets, unions, and intersections. Okay, so let's introduce all of these concepts. A set is a collection of items, and we call those items elements. So, for example, the shoes in your closet at home form a set. The elements of that set are the shoes themselves, right? We usually use capital letters to denote sets, and when we list the elements of the set, we usually put the list inside a set of curly braces, and that's called the roster notation of the set. So for example, if we define P to be the set of primary colors, then the roster notation for P would be, well, the primary colors are red, yellow, and blue. Right, because you can make all of the other colors out of those colors, right? You can make orange by combining red and yellow and stuff. So orange is a secondary color and so forth. This isn't art class, okay, so we'll leave it at that. But that would be the set of primary colors. And the elements would be the colors themselves, red, yellow, and blue. A set with nothing in it is denoted by this symbol, a little circle with a slash through it, and that's called the empty set. So in other words, the empty set would just be this set with nothing inside. If A, little a, is an element of the set capital A, then we use this E symbol. So it looks like a little E, but that means A is an element of A, right? A, or the more common way that I'll read it is I'll say A is in A, right? So little a is in the set A. All right, so again, if P is the set of primary colors, then red is in P, but green is not in P. And that's how we would say that, right? So we put a little slash through it. If this is not an element of that set, then we put a little slash through the element symbol. So let's practice with that a little bit. So this first one says, let A be the set 1, 3, 7, 10. And let's determine if these are true or false statements. So first one says 4 is in A. Is that a true statement? Well, obviously not, right? Because 4 is not in the set. So this is false. On the other hand, 7 is in A, right? 7 is right there. So this is a true statement. And I'll let you do the other 3 on your own. Okay, so here I go. This one's true. This one's false. Kind of tricky, but 10 is in A. So the statement 10 is not in A is a false statement. This one's true. 5 is not in A. Okay? All right. The order that the elements are listed does not matter. So for example, the set red, yellow, blue is the same as the set yellow, blue, red. There are different kinds of mathematical structures where the order does matter, but sets are not one of those, right? So the order in which you list the elements does not matter when you're dealing with sets. And then the other thing about sets is that an element only needs to be listed once in the roster. So if you had a set where you double counted some of the elements like A, B, C, C, B, and D, so C and B are both repeated, that's exactly the same set as just A, B, C, B. And I'm going to call this version like the simplified version. That's not any kind of correct terminology like in set theory. We don't really use the terminology simplified to describe sets. But for the purposes of this class, yeah, I'm going to call this the simplified version of that, right? So where we've eliminated any repeats. So let's do a couple examples. It says find the solution sets to the following equations. We have a couple of quadratic equations here, and you should know how to solve quadratic equations, so go ahead and give the video a pause and see if you can find the solution sets to those equations. Okay, I'm going to work out my solutions now. I'm going to solve this one by factoring. I think I can call this x minus 3 times x plus 2. And then I can apply the zero product property, right? And say, well, if this product equals 0, then one of the factors has to equal 0, right? That's the only way you're going to get 0 when you multiply them. So x is 3 or x is -2. That means that our solution set is 3, -2. And that's how we would write our solution set, right? So the elements of this set are solutions to this equation. If you plug them in, you get a true statement, right? So there's our solution set. On part B, same thing. I can solve this by factoring. This is x plus 2 times x plus 2. So this time we get x plus 2 equals 0, or, well, x plus 2 equals 0. It's the same solution, right? X equals -2 in both cases. So, so one thing that students often do with this kind of problem is they'll say, oh, well, I got x equals -2 or x equals -2. And so they think, well, I need to write -2 twice in the solution set. And you don't, because you don't have to write repeats, right? This is exactly the same set as just -2. On a test or a quiz, if I asked you for the solution set to this equation and you gave me this answer, I would probably mark you down a point, because this is not the simplified version, right? This is the simplified version. There's only one solution to this particular equation, so your solution set should only have one element in it, right? -2 in this case. Very good. Moving on. So let's talk about subsets, okay? So let's say that you have two sets, A and B. We would say that A is a subset of B if and only if every element of A is an element of B. If the set A is a subset of the set B, then we use this symbol. We say A is a subset of B. So this little symbol is the subset symbol. So this is the element symbol. When you have a little line there, when you don't have a line there, then it's just a subset. That's the subset symbol. So here we're saying A is a subset of B. Okay, another way to phrase this same thing is to say if A fits inside of B. So looking at this example, right? It's like A is the set 1, 3, 5. B is the set 1, 2, 3, 4, 5. A is clearly a subset of B here, right? Because each of these elements, 1, 3, and 5, are elements of B as well, 1, 3, and 5. So B contains all of the information that A contains and then some. So that means that A is a subset of B. What am I saying here? So A is a subset of B since 1, 3, and 5 are all elements of B, right? On the other hand, if C is the set 1, 3, 5, and 7, and B is again the set 1, 2, 3, 4, 5, then C is not a subset of B. Do you catch where the issue is? Right? I mean, C is a smaller set than B in the sense that C only has 4 elements and B has 5 elements, but C contains some information that B doesn't, right? C has a 7 in it and B does not. So C is not a subset of B since 7 is in C, but 7 is not in B. Okay, so clearly C is not a subset of B. Okay, so again, right, element symbol, subset symbol. Try not to get them confused. So to help you practice, using the correct symbol, here are some examples. So we have a few different sets. Let's see if we can fill in the blank with the appropriate symbol. So, if I'm comparing the number 2 to the set A, one of the things that I could say is that 2 is an element of A. Right? So I could say 2 is an element of A. It would not be correct. It would not be correct to say that 2 is a subset of A, because 2 is not a set. Right? However, the set made up of the element 2, that would be a subset of A. Okay? So, I guess maybe an easy way to see that is if you don't have curly braces around this, then it doesn't represent a set. So it doesn't make sense to say that it's a subset of another set because it's not a set in the first place. So it can't be a subset. It can be an element though. It can be an element of the set A. And it is, right? But when you put a set of curly braces around it, now this is a set. And now you can say it's a subset of A. Okay? You cannot say that it's an element of A, right? Because this is a set now, right? And the set 2 is not in A. The element 2 is in A, but the set 2 is not. Okay? So with that in mind, you would say here 1 is not an element of A. Also, 1 is not a subset of A. Right? The set 1 is not a subset of A. The elements 3, 5, and 7. 3, 5, and 7. They are all elements of B. So I would say, yes, the 3, 5, and 7 are all elements of B. Is B a... Well, how do B and A compare? We can't say that B is an element of A because B is a set, right? And A doesn't have any sets inside of it. It only has numbers inside of it. So, so maybe B is a subset of A, right? Well, is it? Are all of the elements of B elements of A as well? And the answer is no. There are some overlaps, right? 3 and 5, right? But there are also some things in B that are not in A, like 1 is in B, not in A, right? 7 is in B, but it's not in A. So B is not a subset of A. So I'm going to say B is not a subset of A. 3, the set made up of 3, 8. And we're trying to compare that to the set C. So here's the set C, 3, 5, and 8. 3 and 8 are both in C. But it wouldn't be correct to say that they're elements of C, since this is a set, right? So you wouldn't say that 3, 8, the set 3, 8 is an element of C. You would say the set 3, 8 is a subset of C. Okay. And then finally, you've got C and A. Well, C is 3, 5, 8, 3, 5, 8. Yeah, I would say C is a subset of A. Okay, so so that's how subset notation works. Something to point out, every set has at least 2 subsets, right? The empty set and then the set itself. So if S is a set, then we consider both S a subset of S to be true and the empty set a subset of S to be true. This one is sort of vacuously true, right? Because remember, the definition of a subset is that A is a subset of B if and only if every element of A is an element of B. So the empty set doesn't have any elements. So it is trivially true that every element of the empty set is an element of any other set, right? So it's a true statement. It's a vacuous statement, but it's true nonetheless. And then of course the entire set is a subset of itself because every element of the original set is an element of the set itself. So the original set is a subset of itself. Okay. Sometimes we're interested in knowing what all the subsets of a set are. So, for example, what are all the subsets of the set 1, 2, and 3? So I'll let you pause the video and kind of think about that for a second. See if you can write out all the subsets of the set 1, 2, 3. Okay, here's what I'll say. So first of all, we know that the entire set and the empty set are both subsets of this set. But there are other subsets as well. So I'm going to start off listing them from kind of smallest to largest, right? So smallest, empty set, right? That's a subset. And then we have a bunch of sets that only have one element in them, right? We have all these singletons. The set 1, that would be a subset of this set. The set made up of the element 2. The set made up of the element 3, right? Those would be subsets of the original set. And then we have 2 element subsets, right? 2 element subsets like 1 and 2. Oh, my curly braces are sometimes very ugly. 1 and 3. And 2 and 3. Ooh, I can't even write the number 3. 2 and 3. All right, these are all subsets of the original set. And then finally, we have the entire set, which is a subset of itself. So those are all of the subsets of the original set. We have 1, 2, 3, 4, 5, 6, 7, 8 of them. Notice that we have 3 elements. 2 cubed equals 8. So, and that's not a coincidence, right? So it's always the case that the number of subsets of a finite set is 2 to the power of the number of elements in the set. So, so that's kind of an interesting little fact. Not really useful. We're probably not going to get into that a whole lot more. But that's the idea there. So those are all the subsets. You might be wondering, like, well, what about the set 3, 1? Is that not also a subset? And the answer is yes, it is, but it's already accounted for here, right? Because the order in which the elements are listed doesn't matter. So this is not a different set than this, right? They're the same set. Okay, so that's subsets. Last but not least, we'll talk about some set operations, unions and intersections being some of the most common. So, so let's say that A and B are sets. The union of A and B is denoted with this U symbol. We read this A union B. A union B is the set of all elements that are part of A or B. So in other words, an element is in the union of A and B if and only if A is either an element of A or A is an element of B or both, right? So you get in the union if you're in either one of the sets that make up the union. Okay, so so that's the union. The intersection of A and B is denoted with this little N symbol. So we would read this A intersect B. A intersect B is the overlap of A and B, right? So an element is an element of A intersect B if and only if it's an element of both A and B. Okay, so it has to be an element of both of the sets in order to be in the intersection. So to be in the union, it just has to be an element of at least one of the sets. To be in the intersection, it has to be an element of both of the sets. Okay, this concept, for some reason, is really difficult for students to grasp at first. And I have a feeling it's not because the concept is difficult, it's just because the words that we use to describe it, like it's difficult to describe. But once you catch the concept, once you understand the concept, it's really a pretty easy concept to grasp. So let me try to give you a couple different ways to think about this. So in other words, A union B is the set of elements that are in A or B or both. It's the combination of A and B. Like if you put A and B together and put all of their elements together into one set, that's A union B. It makes sense to call it the union of A and B since we're uniting the elements of those sets, right? We're putting them all together. It's sort of like when two people are joined in the holy union of matrimony, right? All of their earthly belongings are held in common from that point forward, right? Unless they have some kind of prenup, I guess. But anyway, but yeah, union, right? You're putting everything together into one set. A intersect B is the set of elements that are in both A and B. So union is or, intersection is and. Okay, so A intersect B is made up of the elements that A and B have in common. It's the elements where A and B overlap, right? That's A intersect B. And it makes sense to call it the intersection of A and B. It's where A and B overlap. It's like when you have two streets that cross at an intersection, then that little square of road is where it's like both of the streets simultaneously, right? So it makes sense to call it an intersection. Anyway, so hopefully that helps you to kind of get your head around the concept a little bit. Here's a picture to help you even further, right? So these are Venn diagrams, right? So let's say we've got the set A here, we've got the set B there. A union B would be all of it. It would be all of the stuff in both sets, okay? A intersect B would just be the stuff that A and B have in common, right? It's just this little space where A and B overlap. Okay, so hopefully you've got the idea. Here are some examples. Let's say that A is the set 1, 3, 5, 7, 9, and B is the set 1, 2, 3, 4, 5. Let's find A union B and A intersect B. So A union B, this is going to be made up of all of the elements that are in one or the other or both, right? So 1 is definitely in there because it's an element of both sets. 2 is in there, right? 2 is the union. 2 is in the union because 2 is in B. It's not in A, but it's in B, so it's in the union, right? 3 is definitely in there. 4 is in there. 5 is in there. And then 7 is in there, and 9 is in there, right? That would be the union of A and B. You put all of that stuff together. You just don't count the repeats, right? But you put all of the elements in there, throw them in there together, and that's the union. The intersection of A and B. Well, so this would be all of the things that A and B have in common. So if we look at those two sets, they have a 1 in common. So 1 is in the intersection. They don't have a 2 in common, right? 2 is in B, but it's not in A. So 2 is not in the intersection. But they do have a 3 in common. So 3 is in the intersection. They don't have 4 in common, but they do have 5 in common. So 5 is in the intersection. And then, of course, they don't have 7 and 9 in common. So the intersection of A and B is 1, 3, and 5. In terms of the Venn diagrams, you could say something like this. You could say, well, 1, 3, 5 is here in the intersection, right? 1, 3, 5 is here in the intersection. But then in addition to those numbers, A has 7 and 9, and B has 2 and 4. So that's kind of what it would look like. So the intersection is 1, 3, 5. And the union is, well, 1, 2, 3, 4, 5, 7, 9, right? The whole thing. So that's the idea there. Here's another set of examples. I'll let you pause the video and see if you can work these out. Okay. So here are my solutions. A intersect B, I think, is the only thing they have in common is 10. So that would be the singleton set 10. A intersect C, they don't have anything in common, right? So that would just be the empty set. B union empty set. Well, the empty set doesn't have anything in it. So when you're putting all of the elements of B together with all of the elements of the empty set, well, then you're just going to get the set B, right? You're not going to get anything new. If you wanted to use the roster notation for this, then you could say, oh, it's the set 10, 12. But union, like doing B union empty set, the empty set doesn't add anything new. A intersect empty set, on the other hand, now this is just the empty set. Because since there's nothing in the empty set, and since the intersection is all of the elements that A and the empty set have in common, well, there's nothing in the empty set, so they don't have anything in common. So there is nothing in the intersection. The intersection would just be the empty set. In that sense, you can kind of think of unions as additions and intersections as multiplications. And then you can think of the empty set like 0. So anything plus 0 is that same thing. Anything times 0 is 0, right? Anyway, there are some other similarities, but there are also differences between like thinking of unions as addition and intersections as multiplication. It has its limits, right? So you can't exactly use that analogy for everything, but at least as it corresponds to the empty set, that's sort of the idea. Okay, here's another set of examples. Oh boy, this will be a good one. So go ahead and see if you can work this one out. Parentheses work the same way as they do when you're just using normal order of operations with numbers. So you would do this union first, and then you would take the intersection. Whereas on part B, since you don't have any parentheses, you just work this out from left to right. So you do this intersection first, And then once you've done that intersection, do the next one. I suppose you could also just look at it all at the same time and just look for the numbers that A, B, and C have in common, right? But anyway, go ahead and pause the video, see if you can work these ones out. Okay, I'm gonna go ahead and work mine out. So B union C. 2, 3, 4, 6, 8, 9, 10, and 12. Right? I think that gets them all. 2, 3, 4, 6, 8, 9, 10, and 12. Okay. Now I want to intersect that with A. So what does this set and A have in common? Well, they don't have a 1 in common. They have a 2 in common, though. 3 in common. They have 4 in common. They don't have 5 in common, but they have 6 in common. They don't have 7 in common, but they have 8 and 9 in common. So that's my final answer on that one. That's a 3, in case you couldn't tell. And then for part B, oh, let's see. We need the numbers that these 3 sets have in common. So not 1, not 2, not 3, not 4, not 5, 6. They all have 6 in common. Not 7, not 8, not 9. So I think 6 is the only one. Okay. So that's that. Okay. So that's how unions and intersections work. Hopefully that's making some sense to you. One last thing to say here, and then the rest of this is just like, this is just enrichment. Right? This is just math enrichment. Okay, so we'll talk about it, but we'll talk about this stuff, but it's not like stuff you'll be tested and quizzed on. But this last little bit of information is important. Okay, for the most part, we're going to talk about sets of numbers, but we could have sets of other things. As we saw on the first page, I think the first example I gave you was like the shoes in your closet form a set. I gave you another example where you had the primary colors. We talked about the set of primary colors. So you could have sets of things that are not numbers. Some things that are common that will come up again in this course are sets of ordered pairs, right? Ordered pairs are not numbers. They're not real numbers. They're ordered pairs. They're a different kind of mathematical structure. Okay. So for example, let's say that x equals 1 and y equals 2 is a solution to some system of equations, right? So imagine back in your algebra days solving some kind of system of equations by elimination or something like that. And you get x equals 1 and y equals 2, right? You're not getting 2 separate solutions. This is one solution. It's one solution, right? Where x has to equal one number and y has to equal the other number. They have to be set. X and y have to be set to those numbers simultaneously in order for the equation to be satisfied, in order for the system to be satisfied. So this is just one solution. It's a solution, and we write that solution as an ordered pair, 1, 2. That's just the notation that we use to describe this scenario, right? So this quantity right here, this entity, this is not a number, right? It's an ordered pair. Now suppose that -5, 3, and 6, 1 are also solutions to the system. In that case, the solution set to the system would be the set made up of 3 ordered pairs, right? So it's not the individual numbers that make up the ordered pairs. That's not the solution set. The solution set is a set of ordered pairs. There are 3 solutions in this solution set, okay? So kind of a trippy thing to sort of try to wrap your brain around, But yeah, this is not a set of numbers. This is a set of ordered pairs. And there are not 6 solutions in this set. There are 3 solutions in this set. 1 ordered pair, 2 ordered pairs, 3 ordered pairs. Okay? So note, for example, that 1 is not an element of S, right? You might think, well, but there it is. There's 1 right there. But 1 is a real number, and this set does not contain any real numbers. This set contains ordered pairs. So 1 is not in S, 2 is not in S, but the ordered pair 1, 2, that is an element of S, right? So hopefully that makes sense. We could also talk about sets of sets, right? So you could have a set made up of sets, right? So you have the set 2, 3, the set 1, 2, 3, the set 1, 3. And if you make a set out of those sets, you've got a set of sets. Okay? Again, 2 is not an element of A. 3 is not an element of A, but the set 2, 3 is an element of A. So just be aware of that, right? Not all of the elements, not all of the sets that we are going to talk about in this class are sets of real numbers. Some of the sets that we talk about are sets of ordered pairs, right? Or sets of sets. So that's the last bit of information. The rest of this, like I said, is just sort of enrichment. If you wanted to stop watching the video, technically you could, but I think that this is interesting. So I mean, just hang in there and like listen and try to catch on to what I'm telling you for the rest of this stuff. So sets are really useful in mathematics. They're really fundamental to all kinds of stuff that we do in math. But the definition that we've given in this section is really, it's not a very good definition because it's too broad. It's so broad that it causes us to arrive at certain contradictions. And this is particularly a problem when we start to think about sets of sets, right? So for example, we could consider sets like the set A, which is made up of the set of all sets with an infinite number of elements, right? So, for example, the set 1, 2, 3, 4, 5, 6, 7, 8, 9, like on and on and on forever, this set would be an element of A. But the set 3, 4, 7 is not an element of A because this set doesn't have an infinite number of elements. It's a finite set, all right? So if you can imagine the set of all infinite sets, that set we're calling A. So one thing that you'll notice is that A itself has an infinite number of elements in it, right? Think about it. For example, the set 1, 2, 3, 4, 5, 6, 7, on and on forever, that's an element of A. But if you take this set and just get rid of 1, and you look at the set 2, 3, 4, 5, 6, 7, 8, 9, 10, on and on forever, that's a different element than the one that we've written here. But it also has infinitely many elements in it. So that set would also be an element of A. And in fact, you could keep doing that so that you have an infinite number of elements in A. Since there are an infinite number of elements in A, that means that A itself is an element of A. That's kind of crazy to wrap your brain around, but yeah, A is an element of itself, right? That's kind of weird, but that's not necessarily a problem. That's not a contradiction, right? But what I will point out is that most sets don't have this property. Most sets are not elements of themselves. Every set is a subset of itself, but most sets are not elements of themselves. For example, the set 2, 3, 4 is not in the set 2, 3, 4. It's a subset of the set 2, 3, 4, but it's not an element of the set 2, 3, 4. The set 2, 3, 4 is an element of this set 2, 3, and then set 2, 3, 4, and then 4. Right? So that set is an element of this set, but even still, B is not an element of itself, right? So most sets do not have this property. Well, I'm using the word most kind of glibly. Actually, there are infinitely many sets that have this property and infinitely many sets that don't have this property. So it's kind of weird to think about like what does most mean in that scenario. But anyway, but most of the sets that you can probably think of off the top of your head don't have this property. Okay. Nevertheless, some sets do have this property and some sets don't, right? So let's consider the set of all sets that are not elements of themselves, and we'll call this set S. So clearly B is an element of S, right? B is not an element of itself, so B is an element of S. However, A is not an element of S. A is an element of itself, so it's not an element of S. Now for the contradiction. The question, and this question is known as Russell's paradox. The question is S an element of S? Right? Well, if we say no, so we say if we say no, then S is not an element of S. But then if S is not an element of S, then S satisfies the one and only condition necessary to be an element of S. So then this would directly imply that S is a subset or is an element of S, which is of course a contradiction, right? So then you think, okay, so then the answer can't be no, the answer must be yes. But if you say yes, you end up with a contradiction again. Because if you say yes, then you're saying S is an element of S. But if S is an element of itself, then it contradicts the one and only requirement needed for an element to be in S. So if S is in S, then necessarily S cannot be in S. So it's a contradiction either way. If your brain is like melting right now, that's normal. This is a difficult concept to wrap your brain around at first. But grab yourself a bowl of ice cream, sit in a comfy armchair, and ponder this for a little bit. It's kind of an interesting thing to think about. And yeah, you arrive at this contradiction. So the whole moral of the story here is that when we define sets glibly, like we have in this section, we arrive at all kinds of contradictions. And so really, you need a stricter definition of what sets are. And I've provided here a link to one way to define sets so that you don't run into contradictions like this. It's called Zermelo-Fraenkel set theory. And so you can click on that link and look at those axioms if you're interested. It's the reason that I just give this sort of naive version of set theory is because this is really complicated. This would be like for a graduate level math class. So it's just not important to get into it for pre-calculus. I mean, for the purposes of pre-calculus, we're mostly just going to be looking at sets of real numbers. And so you're not going to run into contradictions like this one really very much. Another link that I've given here is to a video that gives a different, it's based on Russell's paradox, but it phrases it in terms of a barber in a town. I'm not going to give it away, but you're welcome to watch that video. In fact, I'm going to provide a link to it in the Canvas module where I post this lecture so that you can watch that as well. It's optional, but it's kind of fun. It's kind of fun to think about these paradoxes. But anyway, that'll do it for section 1.1. We'll see you in section 1.2.